Hello, my name is Evelyn Bateman. I'm a junior in energy engineering, and I recently completed EME 303, Fluid Mechanics in Energy and Mineral Engineering. I've been working on an honors project for the class that is an application and analysis of Betz's law for wind turbine efficiency. In summary, Betz's law states that the maximum theoretical efficiency that a wind turbine can achieve is 59.3% conversion of kinetic to mechanical energy. In this presentation, I will derive the equation that proves Betz's law and hopefully shed some light on a few topics that are explored in EME 303. So a little bit of background on Betz's law before we dive in. In 1919, German physicist Albert Betz published what would be known as Betz's law. Betz's calculations are based on the kinetic energy of wind passing through an actuator disk, or a hypothetical model of an ideal turbine, and we'll talk more about that later. But what we're going to end up doing is deriving Betz's efficiency coefficient of 0.59. Now, while this process might seem a bit daunting, what we'll find is that the calculation can be perfectly understood from our knowledge of fluid mechanics from EME 303. Okay, so let's get started with the problem. This is the model that we will be looking at throughout the calculation. What we have is a perfectly flat, idealized actuator disk in the middle that will represent the turbine for which we are finding the maximum efficiency. The airflow is represented by the curve above the turbine, and we have several variables represented here as well. First, we have our upstream and downstream velocities, u sub u and u sub d. The corresponding area of the flow is written as a sub u and a sub d. The pressures for our upstream and downstream of the turbine are equal and are written as P infinity or ambient pressure. Finally, we have u sub t and a sub t representing the constant velocity of air through the turbine and the area of the disk. P1 is the pressure directly upstream of the turbine, and P2 is the pressure directly downstream of the turbine. Now that we've defined our variables for the calculation, we'll start with a basic continuity identity. We'll begin by assuming a constant volumetric flow rate across the system, and that is to say that Q, which is the velocity times the area of the current, is equal at each of the three locations. So continuity is something that we're familiar with from class, and we'll be exploiting this identity later on in our calculations. So as you can imagine, we have this air current hitting our idealized actuator disk and coming to a stop at the base of the disk. This sudden change in velocity of the air current exerts a force in the disk and experiences a change in momentum. The force can be calculated by multiplying the mass flow rate of air times the change in velocity, and so I think a quick unit analysis here is helpful. We know mass flow rate is in units of kilograms per second, and velocity is in units of meters per second, and so the resulting product is a kilogram times a meter per second squared, which is a newton. Now we can relate this force on the turbine in terms of the variables defined. We can say that a force is equal to a pressure times an area, and in this case, a change in pressure across the disk, P1 minus P2, times the area of the disk, AT. And substituting in for the right side of the equation, m dot is equal to the density of air times the volumetric flow rate, which is AU times UU. And notice we're able to pick an arbitrary point for the mass flow rate expression because we assume continuity. And finally, we multiply our mass flow rate by the change in velocity across the turbine, UU minus UD. Now for the next step, we're just going to divide AT to the other side to get an equation for the pressure drop across the turbine. Alright, now we're already going to apply our continuity equation and swap out the AU times UU in the first equation for AT times UT shown in the second equation. And what we'll find is that the AT cancels out, leaving us with a final equation that I'm going to label equation 1 because we'll be back to it later. The next step here shouldn't be a surprise to anyone in fluid mechanics. We're going to apply Bernoulli's equation between the upstream flow and the turbine flow, and between the turbine flow and the downstream flow, and we're assuming here that elevation changes are negligible, and so there's no z term. So the next step we're going to do is add these two equations together. So there are two things to notice. The first is that P infinity, or the ambient atmospheric pressure, is going to cancel out on both sides of the combined equation, as well as the 1/2 rho ut squared term. So what we'll be left with is this equation. And writing the equation in terms of the pressure drop across the turbine, we end up with equation 2, which we'll be referencing later on. So at this point, I want to touch on a slightly different approach from what we've done so far, and it helps to explain the shape of the flow depicted in our diagram, or in other words, why air expands through a turbine. So we know that turbines convert some of the kinetic energy of fluid flow into mechanical energy. If we write Bernoulli's equation from upstream to downstream, we remember from class that the energy due to a turbine is negative on the upstream side of the equation, or can alternatively be written as a positive value on the downstream side of the equation. So essentially, the energy of the air on the downstream is equal to the energy of air on the upstream minus the energy taken by the turbine. Since we assume that pressures far upstream and downstream of the turbine are equal, they will cancel out on each side of the equation. From here, it is apparent that the downstream velocity ud must be smaller than the upstream velocity. Because of continuity, the smaller velocity means a greater area of flow on the downstream side or expansion through a turbine. So this analysis is just a different and perhaps more familiar approach from what we've done in class, and again, it shows why the airflow has the shape that we see in the diagram. So moving on, we had equations 1 and 2 written in terms of the pressure drop P1 minus P2. Setting these equations equal leads to the following expression. And the next step is to solve for the velocity through the turbine, or ut. And what we'll notice is that the expression can be simplified, and so we will divide here by uu minus ud, and we will end up with the following equation, which I will label equation 3. So all of these equations should start to come together now. We'll define efficiency eta as the ratio of power out of the system over the power into the system. Our job now is to find expressions for the power out of the system via the turbine and the power into the system as the energy of the upstream air. We'll start with the easy part by writing an expression for the power into the system, or the rate of energy in the incoming upstream air. The first equation states that power equals 1/2 m dot v squared, and this equation is very similar to the kinetic energy equation 1/2 mv squared. The only difference is that we're looking at a mass flow rate rather than a mass, and this should make sense because power is equal to energy over time. Now once again, we've defined m dot as the density of air times the volumetric flow rate, or the area times the velocity, and putting these equations together gives an equation for the power of the upstream current. For the purposes of this calculation, we're going to make the assumption that the velocity of air upstream of the turbine is equal to the velocity of the air through the turbine. Substituting ut for uu gives us an extra uu term and results in a uu cubed factor. This is the equation we will use in our efficiency calculation. Now to calculate the power we get from the turbine, or the power out. So this part of the calculation is very mathematical, so it's helpful to pay attention to the algebra, and then by the end we will tie everything together. We've already discussed that the velocity and momentum change when the air hits the disk results in a force. We can write this force as a function of power by multiplying it by a velocity, and once again, a unit analysis tells us that energy is a Newton times a meter, and power is energy per second, so the resulting units are a Newton times a meter per second, or a force times a velocity. We'll substitute the force term for a pressure drop, so P1 minus P2 times the area of flow through the turbine. We're finally ready for equation 1. Substituting equation 1 into the P1 minus P2 term above gives another expression for the power out, which we will see here. Now it's time to utilize equation 3, which I've listed again. Substituting equation 3 into the power out equation above results in this equation for power out. Here we're squaring uu plus ud. So let's take only one of the uu plus ud terms and multiply it by the uu minus ud term. This will give uu squared minus ud squared, and the other uu plus ud term remains. Now we're going to do some factoring of the two velocity terms. First, we're going to factor a uu squared out of the uu squared minus ud squared term. Then we're going to factor out a uu term from the uu plus ud term. The final result is a uu cubed term and a polynomial that we will simplify in the next few steps. Finally, we can plug our expressions for power out and power in into our efficiency expression, and we'll see a few things happen. First, a quarter over a half becomes a half, and second, rho, a sub t, and uu cubed all cancel out, and what we're left with is this equation for eta. To make the math simpler, we're going to make a substitution. We'll set a variable b equal to the downstream velocity over the upstream velocity. Plugging b into the final equation from the last slide gives a much cleaner version of the polynomial that we can FOIL to get this final expression for efficiency. So now we're down to the real task at hand, which is to evaluate the maximum theoretical efficiency for a wind turbine using an actuator disk model. And we're set up to do this now that we have an equation for eta. So to maximize this equation, we're going to take its first derivative with respect to b and simplify. To maximize eta, we'll set its derivative equal to 0 and find its critical points. Fortunately, the derivative is a binomial, so we can apply the quadratic formula, and we'll find that b has two roots, -1 and +1/3. If you plug b equals -1 into our equation for eta, you'll get an efficiency of 0, which doesn't make physical sense. So we will use another root, b equals 1/3. Plugging 1/3 into the equation for eta gives a value of 16/27, or 59.3% efficiency. This is the value that Betz calculated back in the 1920s, and it is still accepted as the maximum theoretical efficiency of a wind turbine in the conversion of kinetic to mechanical energy. That concludes our calculation. I hope you enjoyed my presentation and learned a little bit about the practical applications of fluid mechanics and energy engineering.